So, let's start with muons. So, in our syllabus, it states that we need to be able to describe the presence of muons in the atmosphere as an example of a case where normal Newtonian physics does not apply. So, let's go over what is happening with the muons, why they're in the atmosphere, and why it shows us that Newtonian physics does not apply. So, Newton assumed, Newtonian physics assumed that space and time are constant, that they're uniform and straight. This is a kind of a pretty, I guess, commonsensical assumption to make, right? Space and time are constant, right? So, this is what Newtonian physics is. Space and time are constant, uniform, and straight. Let's get on to what's happening with the muons. So muons are an unstable particle. They're a very, very small particle. We actually learn more about what muons are when we get into the standard model. But they're an unstable particle created when high energy cosmic rays interact with the nuclei of oxygen atoms 15 kilometers above the surface of the Earth. Right? And they have a very, very small lifetime, about 2.196 microseconds. So essentially the situation we have so far is we have a bunch of these tiny little muons, and they're created in the atmosphere because of these cosmic rays. They create them in the atmosphere, and they're really, really tiny. They also move at 99.97% the speed of light, so they travel like super fast. Right? These tiny, tiny particles move super fast. They're created 15 kilometers above the surface of the Earth. This is what we have so far. So, Newton would tell us that the muon's life will end 8.41 kilometers above the surface of the Earth. Right? So, they're traveling really fast, but they have a tiny, tiny lifetime. So they're not going to get to the surface of the Earth. They're not even going to get halfway there from where they were created. And after about 10 lifetimes, there's going to be no muons. So according to Newton, we should really not be able to see any muons, maybe a few, but barely any muons on the surface of the Earth. However, we actually detect a lot of muons on the surface of the Earth. And they actually live 22.8 times more or longer than predicted. So they existed for a longer time period than they should have. Right? So, our situation is we have lots of tiny, tiny particles, muons, created 15 kilometers above the surface of the Earth. They move really, really fast, but they also have a very, very short lifespan. According to Newtonian physics, which says that time and space are uniform and straight and constant, the muons should not be getting to the surface of the Earth. However, we measure a lot of muons on the surface of the Earth, which tells us that Newtonian physics does not apply. Because, evidently, for the muons, the time and space were not constant, uniform, or straight. Something happened to time and space, and something changed the time and space to allow all of these muons get to the surface of the Earth. When according, if space and time were constant, they would not have been able to get there. Alright? In a little bit, we're going to get into what exactly happened to the space and time. But for the moment, let's get on to our next syllabus dot point, which is a few of our defining terms dot points. So the first one is reference frames. So special relativity is based on the relativistic nature of motion. So any motion that is observed is relative to the reference frame of the observer. Right? What this essentially tells us is that motion is relative, and this is a pretty solid and integral part of the actual special relativity theory that we're studying. Motion is relative, right? If I I'm standing on the side of the road and you drive past on the road, you're moving relative to me, because in my perspective, you're driving past. And in your perspective, I'm moving relative to you. Because what you're seeing is you're seeing you stay still and the road and me move past you. Because in your perspective, the car is staying still. Even though I guess logically, you know that you're the one driving. In your perspective, the car is still and the road is moving relative to you. So, what we can say is that a frame of reference is an abstract coordinate system and a set of physical reference points defined by the observer, used for observation and description of physical phenomena. So, this definition kind of sounds like a big, long jumble of words. What I'd recommend is for you to go and memorize the definition provided by QCEE on the syllabus. So obviously, if you find the syllabus online, you can just Control F reference frame, find the definition in the glossary at the end, copy paste it into your notes and memorize that one, because that definition is the one that you're going to be needing to kind of recognize or kind of spit out again on your external. But just for your purposes of actually understanding the term, what this definition essentially means is just a frame of reference is like a person. You know, I have a frame of reference, you have a frame of reference, so forth. Alright. So, the consequences of this is that we can only measure motion relative to an observer, which is what I was talking about before. And secondly, that there is no absolute or motionless reference frame. So there is no kind of starting reference frame or initial reference frame or absolute reference frame. Going back to our car example, the road and earth is not the absolute reference frame, right? Even though kind of to us it might seem like logically, you know, you're driving along the road, so it kind of seems like the earth and the road is the reference frame and you're the one moving, but that's actually not the case. All motion is relative. When you're driving, the road is the one moving relative to you and the car is staying still. Alright, an interesting example of this before I actually quickly move on to the next topic is kind of the classic example of a box, right? Moving through space. If you are in a box with no windows, so you can't see out, right? You don't know if you're the one moving or if the space is moving around you, which is an interesting kind of example of this, right? And in fact, when we get into acceleration and constant velocities, we'll further expand on this example, but we'll wait till we get to that. Next, we're looking at the postulates. So, these are known as Einstein's two postulates if you're ever asked for them in an exam. So Einstein has two postulates for special relativity. The first one is that the laws of physics are the same and can be stated in their simplest form in all inertial frames of reference. So, what this essentially means is that the laws of physics are the same in all frames of reference that are not accelerating. An inertial frame of reference is one that is not changing speed or not changing direction. Or in other words, it's not changing velocity. So An inertial frame of reference could be traveling at 30 meters per second. As long as it is traveling at a constant velocity, it is inertial. If an object is traveling at 30 meters per second in a circle, it is not inertial, because even though the speed is constant, the direction is not, because it's changing direction. Remember, velocity is a vector quantity, so it's a measure of both magnitude and direction. Right. Einstein's second postulate is that the speed of light, c, is constant in a vacuum independent of the relative motion of the source. So, these two postulates can have some interesting consequences. So, proof of the second postulate was shown by Michelson and Morley's experiment in 1887, and the consequences will be discussed later in classes. And then down the bottom here, we just have the actual QCEE definition snipped out if you want to remember that one. Alright, now getting on to simultaneity. So, events are considered simultaneous. I'm not sure why I just pronounced it so strangely. Simultaneous. Events are considered simultaneous if they occur at the same time. This can be difficult to determine if the events are occurring at distances from each other and the observer, and especially if these distances differ. So, we can say instead that two events are simultaneous if light signals from the events reach an observer who is midway between them at the same time. So this is our definition of when two events are simultaneous. I'm not sure what's going on with my pronunciation. So what this essentially means is that if there are two events, an observer standing directly in the middle between them, if they observe light signals from these two events at the same time, this means that the two events were simultaneous. Right? Now, of course, if our observer is standing at the point of one of the events, even if the two events actually are simultaneous, they're going to observe the light signal from the event they're standing next to way before the light signal from the other event. Right? If you're standing next to where a bolt of lightning strikes, you're going to see that bolt of lightning before you see a bolt of lightning that strikes 10 kilometers away, even if they technically occur at exactly the same time. Alright. So, consider the train-car example. Say we have a carriage shown on the left, and a light pulse is given from the center of the carriage. So, a light pulse, when it hits the end of the carriage, opens a door at either end. So, if our light pulse emits from the center and hits both of the doors at the same time, then both of the doors opening are going to be simultaneous events. Now, hang on to this example of the train car in your mind, because we're going to be getting onto this later on when we talk about paradoxes. Alright. Now let's get on to the speed of light. So the speed of light in a vacuum is a universal constant. And we know that nothing with mass can travel at or faster than the speed of light. So, the speed of light in a vacuum is 2.998 times 10 to the 8 meters per second for our purposes. But typically when you're doing calculations, we're just going to simplify that to 3 times 10 to the 8 meters per second. So there are unusual phenomena that occur when an object with mass approaches the speed of light that explain this. Explain why we can actually never travel at or faster than the speed of light. And these phenomena involve time dilation, length contraction, and the relationship between mass and velocity. So, when we're getting into these phenomena, we're also going to be using them to explain the presence of muons in the atmosphere. And we're also going to be exploring about how Einstein's second postulate about the speed of light, c, being constant in all inertial frames of reference in a vacuum, actually has the consequences of these phenomena that I've just listed out. Right? So as you can see, the content that we've been learning about all kind of interconnects. Alright. Sorry, just a quick suggestion. So remember, these terms listed here are mentioned in your syllabus. So if I were you, I would add these into my notes and copy paste the QCEE definition. So remember, you can find those by finding the syllabus online, just by searching physics QCEE syllabus. Control F the document for all of these terms in the glossary, and then copy paste those definitions into your notes or write them down in your notes. It's really important to do this because in your external, if you're ever asked a multiple choice question on a definition, it will say like, out of these 4 options, what is the correct definition for time dilation? It's really useful to actually just know the definition off the top of your head, because the correct answer is going to be the answer given in the QCEE glossary. So if you know that answer off the top of your head, then you won't even have to think about like which of the definitions are right or wrong and thinking about it too much. You can just quickly tick off the one that sounds familiar, and then move on to your other questions and spend your time doing things you haven't been able to prepare as well for, such as like, calculation questions, right? Okay, now let's move on. So now we're getting onto the mass effect. So, Newton's second law of motion suggests that as long as there is an unbalanced force, that an object will continue to accelerate. However, we know that the above is not actually always true. How is this so? When we continue to accelerate, or when we continue to put an unbalanced force on an object, we're applying a force. At a certain point, it will actually kind of stop accelerating as much, right? So even if we're applying the same amount of force, or kind of, the same amount of, the rate of increase of the force is the same, the acceleration will actually decrease, right? So, as an object gets faster and faster, even if we keep putting more and more force into it, trying to get it to go faster, it will actually kind of lose the ability to go faster. And as we're putting force in, what we see is that the mass of the object actually increases, which is kind of crazy, right? So if you're trying to accelerate an object and it's getting close to the speed of light, as it's getting closer to the speed of light, the energy that you're putting in to accelerate is actually going to not even go towards accelerating it, but actually go towards making its mass bigger, right? So it's going to be accelerating less and getting bigger. Which, yes, again, sounds crazy because it's like, you can't kind of just increase the mass of something by putting more force into it, but this is what we observe. So, what we can tell from this then is that mass is also a relativistic property, which means that mass can be different when observed by in different frames of reference. It can be different relative to different observers. It's a relativistic property. So, we therefore have two values, m0, which is the rest mass, or the invariant mass, and this is the same in all reference frames, and m, which is the relativistic mass, and this is the mass in the frame at which the object is moving at velocity v. So, say you have a particle flying around a room, going very, very fast. Say we've captured a muon, right? The rest mass is going to be measured by a person, kind of, say an imaginary, very small person, standing on top of the muon and traveling with it. The relativistic mass is going to be measured by a scientist standing in the room watching the muon whizzing about, because that is the frame in which the object is moving. For the person, the tiny person standing on top of the muon, to them, the object, the muon, is not moving. The muon is staying still, the world around them is moving. Right. So, we actually have a formula for determining the mass effect based on the relative velocity of the object compared to the speed of light. So, as you can see, we have m, or the relativistic mass, is equal to the rest mass m0 divided by the square root of 1 minus the velocity of the object v squared divided by c, which is the speed of light, squared. I'll bring that in quickly. This should be a squared up here, not a squared down there. So as you can see, the relativistic mass is always greater than the invariant mass. And this is because when we are dividing here, we are dividing by kind of a number which is making our relativistic mass greater, right? So we are dividing this number here, we're dividing by a small number. So when you're dividing by a small number, you end up with bigger pieces. Think about it like this. If you have a pie and you cut it in half, you end up with big pieces. You're only dividing it by 2. However, if you cut up a pie into 100 pieces, you're dividing by a big number, you're going to end up with tiny, tiny slivers, right? So the bigger the number you're dividing by, the smaller pieces you're going to be left over with, right? The smaller the number you're dividing by, the bigger the pieces you're going to be left over with. So because we're dividing by a small number, we're going to be left over with a bigger number over here. So from this we know relativistic mass is always going to be greater than the rest mass. So The relationship of mass increase as velocity approaches the speed of light is exponential, which I'll show you guys over here. So, as the velocity of the object approaches the speed of light, its mass approaches infinity. As you can see here, its mass is kind of fairly stable, when it's traveling at lower speeds over here. But as we kind of get to around, maybe 0.5, the speed of light, what you can see is that the mass is increasing exponentially. And at c equals 1, this line here, what you can see is that our line actually never gets there. So it's approaching c equals 1 asymptotically, right? It's getting closer and closer and closer there, but it's never actually reaching it. So what you can see from this is as speed increases, more of the force going towards accelerating, the mass is actually going into increasing the mass. So now let's get on to our next topic of phenomena, and this is time dilation. So time dilation is the cause of the moving clocks run slow phenomena. So, time is relativistic, i.e., the time interval between two events cannot be the same for two observers that are in motion with respect to one another. So, gravity bends space-time. Therefore, time moves slower in regions of increased mass. The mass of an object will increase significantly as its velocity approaches the speed of light. Hence, its gravity increases and elapsed time slows. Another way to think about this is kind of as a consequence of Einstein's second postulate. So, thinking about the speed of light always being constant for an inertial observer in a vacuum, right? If two observers are seeing the same light, they're going to see that light as traveling at the same speed. However, if those observers are traveling at different speeds themselves, yet they're still seeing the light travel at the same speed, this is going to have consequences on the time experienced by both of those people. So, classic example of this is the light bouncing between mirrors. So say we have a train, right? A person is on the train, and the train is moving in this direction at 0.95 of the speed of light. It's traveling very, very fast. This, of course, is a hypothetical situation. We do these experiments like actually in real life, and of course, we can never get anything that of that significant mass traveling that fast, but we can get them traveling fast enough that with super precise instruments, we can actually still measure the differences. But of course, this is just a hypothetical. So, this person on the train is observing light bounce between these mirrors. So we have these mirrors, and we have light bouncing. Actually, no, make it even a little bit. Change this a little bit. Say we have two mirrors, and we have light bouncing back and forth between these two mirrors, right? Might even draw that as yellow. So this person is on a train and he is seeing the light bounce back and forth between these two mirrors. Now, say we have a person on the station. He is not moving, he's just standing on the station. And he is looking at this scenario. Alright, to him, he's not just seeing what's happening inside the train, he's also seeing the movement of the train as it's going past. So, instead of seeing just the light bouncing back and forth between those mirrors, what he's seeing is, and I'll just draw it off to the side here, he's seeing the train move as well, right? He's seeing the train moving, and as a result, the mirrors moving. So what he's seeing is the light actually bouncing back and forth like this. Instead of going back and forth over itself, like the red person is seeing, he's actually seeing the light move forwards as well because he's observing the whole train moving forwards. So, now let's think about Einstein's second postulate. So if both of these observers are inertial, say they're also in a vacuum, they're seeing that light move at the same speed. From both of their perspectives, the light is moving at c. Have a think about where this might give us some issues. For the person on the train, the light is moving back and forth this distance here. For the person on the platform, the light is traveling farther, right? Because instead of just going back and forth here, it's actually, and I guess you can prove this mathematically, but I won't go through it now. See, we actually have, this is where the mirror would be that the person on the train is observing. So as you can see, the light is actually traveling along the hypotenuse instead of along this line here, which is what that red person is observing. Remember, the hypotenuse is always the longest side of the triangle. That's proven mathematically. Pythagoras' theorem, right? So the blue person is observing the light travel a longer distance, but he's still observing it travel at the same speed. So what happens as a result is, out of a few other different phenomena, but one of them is happening as a result, is time dilation. Right? So, to make up for this, this person is going to see events occurring in a different time to this person. So, this person is going to experience time normally, this person is going to experience time normally, but when they're looking at each other, they're going to look at each other and go, wow, that person's time is whack. Right? So they don't feel like they're in slow motion or anything, but they're looking at each other and going, wow, that other person's time is just off. Right? If our blue person is looking at our red person, this red person looks like he's in slow motion. Right? It looks like this red person is experiencing time slower. And the reason for that is because we need to allow more time for this light to travel a greater distance in this blue person's perspective. Because they're seeing the light travel a greater distance at the same speed, right? They need to allow more time for that travel to occur. So if they're seeing more time in the carriage, they're also seeing the red person in slow motion. They're seeing everything else happening in the carriage in slow motion, right? But the person on the carriage is not experiencing anything in slow motion. They feel normal. When this red person is looking out to the station, they're seeing the blue person move about faster than normal. So comparatively, he's seeing the blue person move around faster. Even though both of them feel normal within themselves, when they're looking at each other in that different reference frame, they're seeing a difference in time. Alright, let's move on to our time dilation formula. So, time dilation is maximal when the velocity equals c. So when the velocity equals c, the elapsed time is 0. So at velocity equals c, time stops altogether. Right? It's good that light doesn't actually experience time, nor does it have any mass, which is why light can travel at the speed of light. Right? Alright. Looking at our formula down here, again this one is on your formula sheet too, we have T0 being proper time and T being dilated or relativistic time. So proper time is a time measured in the frame in which kind of like the movement is happening. And dilated or relativistic time is the time measured in the frame of the observer. So if we had a rocket take off, the clock on the rocket would be measuring proper time, and then the clock on Earth would be measuring relativistic time. Alright, now let's get on to length contraction. So this is another one of the phenomena. And we'll go back to our train light mirror example to further explain this as well. So, length contraction is a phenomena wherein the length of an object actually contracts in the direction of motion. So, we have our two values, L0 and L. L0 is the length of those on Earth or not moving, it's the proper length. And L is the length of those moving in the frame of reference, the relativistic or dilated length. So, if we have a rocket traveling from Earth to planet Rigel, then in the frame of Earth or Rigel, the distance traveled is going to be L0, the time is going to be t, and the velocity is v. In the point of view of the people on the spacecraft, the distance traveled will be L, the time for the journey will be t0, and the velocity will be big V. So as you can see, for the spacecraft, if they want to travel the distance and kind of do it in, I guess, relativistically a shorter time frame, they can travel faster. Because if they do that, then the length that they travel will seem shorter, and the time that they travel in will also seem smaller. Right? So, in summary, the relationship between velocity, length contraction, and time dilation is below. This formula is, of course, just coming from velocity equals displacement over time. Length is just displacement here. As you can see, we have a quick diagram on length contraction. As our velocity is increasing, our object is contracting in length in the direction of travel. So as you can see, the height of the shape isn't changing, but because it's going in this direction, it's getting skinnier, right? And then this formula here describes the relativistic length and the length of the, oh, sorry. There we go. Alright, now getting on to light as the universal speed limit. So, it should kind of be clear now why light acts as the universal speed limit, and why nothing with mass can travel faster than the speed of light in a vacuum. So, as the object approaches the speed of light, its mass approaches infinity, its length approaches zero, and the elapsed time for a given period approaches zero. So, we have all of these formulas to describe these phenomena, and as a result, nothing with mass can travel at or over the speed of light. There is actually one, I guess, not even exception, but I discussed kind of like interesting fun facts to know, is that there actually is something that can travel faster than the speed of light. And it's nothing with mass. It's not an object. It is actually the meeting of the two blades of scissors, right? If you're closing those scissors, if you close them super fast, that point where they meet can actually travel at faster than the speed of light, which is interesting. But of course, that obviously doesn't have mass. It's just like a point. It's not even like an object or anything like that, like you might describe light as if you're talking about it as a photon. So just something interesting to know. Alright. Now getting on to mass-energy equivalence. So, anything with mass has an equivalent amount of energy. Anything with energy, an equivalent amount of mass. So, we can use our formula E equals mc squared to determine the relationship between energy and mass. So, the primary consequence of this relationship is that an object at rest has intrinsic energy, or rest energy, that corresponds to its rest mass. And when the object is in motion, its relativistic mass is greater than its invariant mass, because there is more energy, because it's in motion. Right? So, this is how we use our mass-energy equivalence. We can also use this formula when we are getting into quantum theory, but it just helps us for the moment in determining the relationship between mass and energy. Alright, now we're getting on to the end of our syllabus for special relativity. And we're getting onto the three paradoxes. So, there are three paradoxes you need to be able to explain and describe. So, a typical exam question might just be, explain the twins paradox, right? And you just need to be able to rattle it off the top of your head. So what I'd recommend for learning these is, once you understand them, write a short kind of 3-sentence explanation in your own words. Try to make it really concise, and then memorize that on a flashcard. So, let's go through the twins paradox. So, say we have two identical twins, one of which makes a journey into space in a high-speed rocket. Upon returning, he notices the twin on Earth has aged more. So, Consider an application if inertial reference frames and time dilation. Each twin has observed the other in motion, so should have found the other to have aged less, but this is not so. So both of them have been in motion. In both of their perspectives, the other moved away from them and then moved back towards them at a fast speed. Remember, moving clocks tick slower. So both should have observed the other one to have aged less. But what we see is that the twin who went on the spaceship aged less and the twin on Earth aged more. So, what is the explanation for this? Does this prove a hole in Einstein's theory? Have a think about it. Please pause the recording if you've already learnt this and try to remember the solution. If you haven't learnt this, pause the recording and try to think of the solution. But I'll go to the solution in 3, 2, 1. So, essentially what we have is that one twin goes out in space, comes back, and is younger. The twins were in constant motion relative to another, and both see each other aging quicker. The key is, or the solution, is that only one twin spent the entire time in an inertial reference frame. So the twin on the spaceship actually accelerated away from Earth, then got to the planet, turned back around, so it changed direction. Presumably it slowed when it got to the planet too, and then when it got to Earth it slowed back down to land. So, Einstein's theory only deals with constant motion. It doesn't deal with accelerated frames of reference. That's why in all of our definitions we're talking about inertial frames of reference, which are ones that don't accelerate. In other words, they have a constant speed and constant direction. So, our spaceship twin actually accelerated. Right? So have a think about this. Which twin's frame, therefore, measured proper time, and which measured relativistic time? Have a think about it. Alright, getting onto the flashlight on a train paradox. So this is the next paradox you need to know. So, imagine a person on a train in constant motion with a torch. He shines it at a mirror on the other side of the carriage, the distance that the light beam travels. From the distance the light beam travels from the frame of reference of someone on an embankment watching the train go by, the light travels a shorter distance. How is this possible, knowing that the light cannot travel faster than c? I'm just going to draw a quick diagram of this. So, for the person on the train, what he's seeing is the light from the torch to the other side of the carriage. Right? And the carriage is moving in this direction. Alright, from the perspective of the person on the embankment, what they're seeing is the carriage and they're seeing the back of the carriage move towards the light source. right? So they're seeing this light source, but they're seeing the carriage move towards this light source and the light move towards the carriage. So what they're going to see is the light moving a shorter distance. So, how is this possible knowing that the light cannot travel faster than c? Pause the recording, see if you can explain it. And the hint is simultaneity. Alright. So, essentially, consider time dilation and simultaneity. The speed of light remains constant, but the events simultaneous to one viewer isn't simultaneous to another. The distance the light had to travel depends on your reference frame. So, the train moving close to the speed of light influences this, even though the person on the embankment and the person in the carriage sees the light hit the end of the carriage at different times. Oh, sorry. Just because they see a shorter distance, right? Simultaneity is relative based on reference frames. So that is the solution. Alright, now getting on to the last paradox, which is the ladder in a barn paradox. So, for this one here, we have a ladder or a pole, whatever you'd like, parallel to the ground, moving horizontally to the ground at a relativistic speed, or in other words, near the speed of light. So it is undergoing a length contraction and moves through the barn that's length is shorter than the ladder's rest length. So, to a stationary observer, the ladder can fit inside. But to an observed moving with the ladder, there is no length contraction of the ladder, and it is instead the barn that is contracting. Or in other words, the ladder can't fit. Right? Can anyone explain? Let's draw a quick diagram of what's occurring here. So, we have from a person watching, from their perspective, we see a barn, and we see the person running in with a ladder shorter than the barn because they are moving at a relativistic speed, say 0.9 c. So the person outside is seeing the ladder being contracted to be shorter in the direction of motion. However, in the person who's running's perspective, what they see is the barn contracting and their ladder being the same length. I'll just quickly draw. See the rungs are close together here, but for the person running, what they're seeing is the ladder not contracted, and they're seeing the barn being contracted. Right? So how can the ladder fit inside? The observer sees the ladder fit inside, but from this person's frame of reference, the ladder is never going to fit inside because it's too long. So, who's right? What is the solution? Right? How can it be that in this person's frame of reference, the ladder fits in, but in this person's frame of reference, it doesn't? Does it fit or does it not fit? What's the answer? Alright. The solution is that simultaneity is relative. So just because two events are simultaneous as measured from one frame of reference, It does not mean that they are simultaneous from another frame of reference. So, the doors being opened and closed are not simultaneous events from the frame of reference of the pole. So, going back to our diagram, if we have a door at either end of these barns, right? And then, so in this person's frame of reference, the person running in can fit in with both of the doors closed at the same time. From the frame of reference of the person running, the doors cannot close on either end simultaneously. But the doors closing can be simultaneous in one frame without being simultaneous in the other. It's all relative. Remember? So on this person's frame, what actually they see is they see this door opening. Then while they're inside the barn, right, this door is opening, right? So the doors opening and closing are not simultaneous. The door closest to them is opening first, and then the door furthest from them is opening second, and then this door is closing again behind them, and then this door is closing behind them. So the doors opening and closing are not simultaneous events, even though they are in the frame of the person watching. Alright,